Hello, chemists! This is Ms. Placino, and you're watching Lesson 8.1, An Introduction to Nuclear Chemistry. Today we're really going to focus on why nuclear decay occurs. So some goals for today's lesson. You should be able to explain what occurs when a nucleus undergoes radioactive decay. You'll recall properties of decay particles. And you'll be able to predict the type of decay that a radioisotope will undergo. All right, let's dive right in. So in this unit, we're going to be studying nuclear chemistry, which is really a big change of pace from what we've been doing up until this point in time. So far in chem, when we're looking at chemical changes, we're really focused on the electrons. We know that those are the subatomic particles that are going to get involved in things like bonding. They're going to be moved around when chemical reactions occur. They're really kind of what give an element its properties. As the name suggests, we are going to be studying the nucleus of the atom. We're also going to look at nuclear reactions, such as fission and fusion, and look at the products that are produced as a result of these nuclear changes. So, huge shift in focus. It's going to be all about the nucleus, the protons, the neutrons, and we are basically going to ignore that electrons are even present as we really embark upon this unit. Today we're going to be looking at radioisotopes. What do you think that word might mean? We should know what isotopes are. Isotopes are versions of an element that have the same number of protons but different numbers of neutrons. What do you think radio might refer to in nuclear chemistry? Yeah, it's short for radioactive. So our radioisotopes are unstable isotopes. And that is going to be because we've got a nucleus that is going to undergo some sort of radioactive decay. And we're going to be focusing on these for this lesson and kind of really what makes that nucleus unstable and what sort of decay will the radioisotope undergo in an attempt to lead to a more stable nucleus. All right, before we dive into any specific problems, I want to review a little bit about formatting. So here we've got a symbol and a couple of numbers. Hopefully we know that that capital U, if we're talking about an element, is the atomic symbol. That's going to tell us the name of the element we're working with, or the symbol of the element we're working with. U, as you may or may not know, is uranium. What about the number on top, this 238? Do you remember what that refers to? I know it's been a while since we've talked about the nucleus. Yeah, that's the atomic mass. So that's going to be the total sum of the protons plus the neutrons. Really, the mass of the nucleus. And finally, that number 92 at the bottom, what might that be? This is atomic number. That's telling us how many protons are in the nucleus. You will almost always see like the symbol and the mass, but sometimes the atomic number is missing in notations. The reason for that is, well, if you're looking at uranium, it has to have 92 protons in its nucleus. So don't be surprised if you see that number missing. I would encourage you, as we're just kind of getting started on this and we're starting to write equations, whether they're natural or artificial transmutations, it's probably a good idea for you to include both values. That's just going to make it a little bit easier for you to keep track of the subatomic particles. All right, so I want to start by looking at spontaneous or natural transmutations. What does the word transmutate mean, or transmutation? I'm guessing you know what the word mutate means, or you've heard it before. Talking about turning into something else. When we're looking at transmutations, we're talking about one element or atom turning into a different element or atom. This can only happen by changing the number of protons in the nucleus, so this is going to require some sort of nuclear change. When we talk about a transmutation occurring spontaneously or occurring naturally, these are going to be nuclear changes that we don't do anything to start. They just kind of happen on their own due to inherent instability in the nucleus. So we'll keep kind of reminding you about those terms and coming back to them again and again. So why does this occur? Why do we see an atom turning into another atom? It has to do with this ratio of neutrons to protons. Certain combinations or certain ratios of neutrons to protons are just inherently unstable. the nucleus is going to undergo some sort of decay. And we'll talk about the different types of decay that may occur to improve the ratio to something more stable. So there are just certain nuclei where it's an unfavorable number of protons to neutrons. Sometimes there's too many neutrons, sometimes there's too many protons, sometimes the nucleus is just simply too big, but it makes it unstable. So we're going to see changes occur to try to stabilize that nucleus. You might be wondering, well, what is the purpose of the neutrons? We know that the protons are positively charged. They're going to help to balance out the negative charge of the electrons. What are the neutrons doing? They're neutral. It has nothing to do with charge. Well, think about it. You know all protons have a positive charge. But all the protons in the nucleus, that's a lot of positive charges that are forced to be very close to one another. And you know from experience that like charges tend to repel. You can think of the neutrons as helping to spread out the protons and just kind of distribute the positive charge. Sometimes if there are too many neutrons, it's just kind of, charges are too far apart from one another, and that's not particularly stable. If there are too few neutrons, too many positive charges are too close together, that's not stable either. You've got this graph in your workbook. We've got atomic number, or number of protons, on the bottom. And then we have number of neutrons running along the y-axis. So we take our atomic mass minus the atomic number to get neutrons. This series of dots that we see here, this is known as the band of stability or belt of stability, depending upon what resource you are reading. And those are kind of showing us the ratio of protons to neutrons that end up being stable, giving us our nuclei that have a favorable number, or favorable ratio, I should say, of protons to neutrons, where we will not see decay. So these are not radioisotopes. You can see that as we have like really low molar mass atoms, a 1-to-1 ratio of protons to neutrons is stable. But as the atom becomes bigger and bigger, or more specifically, the nucleus becomes bigger and bigger, we need more neutrons present to help stabilize the nucleus. Kind of see that trend throughout. Instead of that like diagonal line, we've got it kind of arching upwards. So let's kind of talk a little bit more about this graph. What I'd like you to do is label the line where protons equal neutrons. Yeah, so it's going to be that diagonal line stemming out from 0. We're going to draw a line at atomic number 83 from the x-axis to the top of the graph. So 83, you can kind of just ballpark it. I know it's difficult to try to divvy that up exactly. As a result, now we've taken this graph and we've cut it into 3 sections. So we've got kind of like above the curve, generally speaking below the curve, and we have everything that's like to the right of the curve. And what we're going to be able to do by the end of the lesson is predict what sort of decay is going to occur in each of those sections. And we're going to look at really alpha, beta, and positron decay as changes that can occur in the nucleus that also changes the identity of the nucleus. All right, so again, we're looking at spontaneous or natural transmutations only. This is not fission or fusion. These are radioactive isotopes that are going to just naturally decay and release decay particles. So we're going to focus on the type of particles that could be released. Up first, we'll have alpha decay. That's a symbol alpha. You might also see a helium nucleus, 4,2He. When alpha decay occurs, the nucleus is going to emit 2 protons and 2 neutrons that have been fused together, effectively a helium nucleus. So we have our original radioisotope. It is unstable. We have an unfavorable number of protons to neutrons. So we're going to eject our alpha particle, and then we have our new element. That's fundamentally changed because we've lost 2 protons. So that's going to change the atomic number, hence the identity of that nucleus. This occurs when the nucleus is just too big. And these alpha particles that get emitted, they have a very low ability to penetrate. In other words, if you got hit with some alpha particles, they're not going to be able to get past your skin. Please don't misunderstand into thinking that alpha particles are not potentially dangerous. You can get alpha burns. You can imagine if you somehow ingested or inhaled something that emits alpha particles, the particles can't escape your body. But associate alpha particles with a low ability to penetrate. We also can have beta decay. We have our symbol beta minus. You also might see 0 minus 1 E. That looks like an electron's being emitted. In beta decay, we have too many neutrons. Basically, the neutron, or one of the neutrons, will turn into a proton to keep the charged balance, and an electron gets emitted. So again, we have our original nucleus. Beta decay occurs, an electron is ejected, and that's because a neutron has now turned into a proton. Again, this will change the atomic number, so we end up with a new nucleus. Again, this happens because there are just too many neutrons in the nucleus. And a beta particle, which is really just an electron that's emitted from the nucleus, has a medium ability to penetrate. Basically, it can be stopped by cloth or like aluminum foil. Next, we have gamma decay. Sometimes you'll see it like that, with no mass and no charge. Gamma decay is really just energy being emitted. So in this case, we have our original nucleus. It's emitted a gamma ray, which also could just kind of be considered a photon. And you can see that no change has happened to the nucleus. It's still the same identity, just lower energy. This occurs when the nucleus is too energetic, and a lot of times gamma decay will accompany another form of decay. Gamma decay has a very high ability to penetrate. It's got no mass and no charge, so it's just energy, and it can only be stopped by something like concrete or lead. You need a very dense material to protect yourself from gamma radiation. Up next, we have positron decay. Positron decay might also have this symbol. And you might be looking at that saying, well, that's kind of weird. It's got no mass, a charge of +1, and the symbol of an electron. Yeah, positron is a type of antimatter. It's basically a positively charged electron. Positron and beta decay are opposites of one another. In positron decay, a proton turns into a neutron, and this positively charged particle, a positron, is emitted. So again, we've got our original nucleus. A positron is emitted with a charge of +1, no mass, and we see a change in the atomic number again. We get a new element, as one of the protons has turned into a neutron. This occurs when there are just too many protons in the nucleus, not enough neutrons. And like a beta particle, it has a medium ability to penetrate. Those are the four big different types of decay and decay particles to worry about. We've got alpha, when you've got a really massive nucleus. Beta decay, when you have too many neutrons. Positron decay, too many protons. And gamma decay often accompanies one of these changes, as there is just too much energy in the nucleus. There's one last one that I'd like to talk a little bit about, mostly just because I think it's pretty interesting. It's electron capture. As the name suggests, this nuclear change occurs when an electron in one of the inner shells is sucked in or captured by the nucleus. So the nucleus is going to pull an electron in. As you might guess, that negatively charged electron is going to be attracted to a proton, and effectively a proton plus an electron will give us a neutron. So in this case, instead of emitting an electron, our original nucleus is going to capture an electron, again changing its identity. We get a new element. Okay, So this also occurs when there are too many protons in the nucleus. It looks very similar, the change of a positron decay. And we don't have a particle being emitted, so we're not going to see some sort of penetrating ability for electron capture. All right, so let's get back to this graph where we have our band of stability, all these dots. We have the three different sections of the graph, 1, 2, and 3. We want to try to get these labeled as far as what sort of decay will occur. Personally, I think number 3 is the easiest one to start with. 3 applies to all nuclei that have more than 83 protons in their nucleus. So this is a big, massive nucleus. Based on that information, what sort of decay do you think you'll see? Hopefully you're thinking alpha decay. That's going to happen anytime you've got that big nucleus. This is the fastest way to kind of shrink down the size of the nucleus by losing both 2 protons and 2 neutrons. So that really leaves section 1 and 2 to be either beta or positron decay. If we're up here, just to kind of pick an extreme situation, I've got about, I don't know, maybe 25 or so protons and about 80 neutrons. That sounds like a lot of neutrons. Yeah, above here we have too many neutrons. If you have too many neutrons, what sort of decay are you most likely to undergo? This is going to be beta decay. By process of elimination, section 2 must be beta plus or positron decay. But think about it. If I've got, 40 protons and 20 neutrons, that seems like a lot of positive charges and very few neutrons to space it out. So positron decay makes sense here. This is also the section of the graph where potentially you could see electron capture, but these are the 3 big ones to be aware of. If you're feeling a little shaky on trying to remember those different notations, New York State feels your pain, you can always check table O for the symbols. All right, you got some practice problems helping you review different characteristics or properties of our particles and making some predictions on what sort of decay will occur. So definitely give those a shot. When we come back next time, we'll start being able to write decay equations for these natural transmutations. Good job today, chemists. Thanks for tuning in, and I hope you found this helpful.